The peaceful and awe-inspiring Appalachian Mountains offer us so much to appreciate. And if you are observant, you will see hints of great forces that uplifted these mountains.
Hello, I'm Myron Cook. I'm excited to talk to you about the Appalachian Mountains. You know, I think they're an underappreciated mountain range. And I think it's likely because they don't have these tall, rugged, snow-capped peaks like you get in the Rocky Mountains.
Yet the Appalachians have an amazing beauty about them.
And also, I hope to show you have a phenomenal geologic story behind them. The building of these mountains and the subsequent erosion had a profound effect on North America. Just as a quick example that we'll get into more detail later, did you know that there was this basin along the western flank of these great mountains that was profoundly deep? It was almost like a giant hole. And I say that because it filled with some 45,000 feet of sediment. You heard that right, 45,000 feet. That's 8.5 miles. Now that's some deep basin, isn't it? To start this geologic story, let's dive into plate tectonics just a bit. Now I know that most of you, maybe even all of you, know a fair bit about plate tectonics. But you know, even as a geologist, it's hard to comprehend what's going on with plate tectonics, to fully grasp it. After all, we're talking about these huge plates that raft around on the Earth's surface, colliding with each other, creating mountains, sometimes diving under each other, which often create volcanoes, or maybe pulling apart and creating great fissures. Wow, it's a bit overwhelming, isn't it? And you might wonder, how could this even be? It took geologists a long time to accept that theory. But you know, what I've found useful sometimes in these kinds of situations when we're talking about such large-scale processes and giant features is to scale everything down to a size that we can kind of intuitively feel it better, I like to say, to understand it. So with that in mind, I want to show you something. I have here this exercise ball, and of course it's supposed to represent the Earth. It's 25 inches in diameter, whereas the Earth is some 7,900 miles in diameter, somewhere around there. So I've scaled this way, way down. Now the continental crust on the Earth is about 25 miles thick. It can be up to 40 miles or so thick. The oceanic crust is only 4.5 miles thick. So now I have a question for you to ponder. Now that I've scaled this down, the Earth down to 25 inches, how thick would that continental crust be, this 25 miles? How thick would it be here on this? Have you got something in your mind? Have you got a thought? Let me show you. It turns out that it's 11 pages of printing paper. Yeah, 11 pages of printing paper. Now that is thin, isn't it? Well, what about the oceanic crust? Well, it is exactly, of course nothing's exact, 2 pages of printing paper thick. That's the thickness of the plates that would be moving around on this scaled model. They seem rather fragile, these tectonic plates, don't they? Now it's a lot easier to imagine this crumpling and diving under and moving around each other and moving around on the surface of the globe, isn't it? At least it is for me. Now, with this hopefully better perspective of plate tectonics, let's move on to the amazing geologic story of the Appalachians, shall we? Well, I have my whiteboard here to help us out. Let's go back in time some 500 million years ago, shall we? This is kind of what the world looked like from a plate tectonic perspective. We're looking at a cross-sectional view. We've got the little volcano here and whatnot to show us that. But this is continental crust here. This would represent the continental crust of the eastern United States where the future Appalachian Mountains would reside. And the red is oceanic crust. And of course, we have some volcanics that I'll get to here in a minute. Now, also keep in mind we have the mantle, which is about 1,800 miles thick. It's very hot, but it's not molten. It's more like maybe a caramel or asphalt. It's very viscous fluid. It flows. On geologic time, it flows fairly readily. But anyway, it flows some. And we have all the heat involved from the core and within the mantle that drives convection currents. You know, these currents in here that drag these plates around. Now, hopefully, with the scaled model I showed you, it helps us think about that and helps us think that, oh, that could happen very easily. This is like a film almost on the Earth. It's so thin and so fragile in some ways. So here we go. We have oceanic crust here attached to the continental crust that is subducting underneath this oceanic crust. And of course, when that happens, as you know, in plate tectonics, that melts the rock, especially with more water involved, and it comes on up off here, coming up, creating volcanoes, and through time thickens the crust some here. And of course, these volcanoes can erode and form rivers and have their own environment and create land masses, essentially. Now, we call these, along this subduction zone, when you have these volcanoes like that, a volcanic arc. And I'll show you that here in map view in just a second. So let me show you the motion of these plates relative to each other. This one and this diagram going this way, and this plate, meaning this section here, coming this way. Of course, that means these two are going to collide, doesn't it? It turns out to form the Appalachians, there were three major collisions that occurred after the formation of this basement rock. This basement rock, by the way, is 1.1 billion years old. That's what sits underneath everything. And I won't get into its formation, but after the formation of this basement that sits here, exactly three major collisions occurred. The first one was the Tectonic orogeny, which I've sketched here. This collision that's going to occur at 460 million years ago in the Ordovician and formed the early stages of the Appalachian Mountains.
So now looking at this in map view, we see North America some 500 million years ago in the late Cambrian. The name of the continent at the time was Laurentia. And notice that much of North America was covered in water. In fact, the United States was almost entirely covered in water. I've highlighted Pennsylvania here for reference. Now, along this heavy black line is the subduction zone that I sketched out in the cross section. Now, to the right of the subduction zone is this long chain of islands, and this is the volcanic island arc that I mentioned. And in fact, these are the islands that were rafting along, heading towards the east coast, that we're going to accrete or plaster onto in the Tectonic orogeny that we've talked about. The ocean at the time was called the Iapetus Ocean. The Atlantic Ocean was not to be for a very long time. Let's jump forward in time to 450 million years ago in the late Ordovician, which is after the volcanic island arc had accreted onto North America. Focusing in to the east coast, we see a mountain range that had formed, which of course is the early Appalachians. For the first time, we have land to the east of Pennsylvania. Looking carefully along the west side of the mountain front, we see a finger of deeper water. Now, this basin of deeper water is what geologists refer to as a Foreland Basin. We will discuss this further shortly. Now look what we see to the east. Another subduction zone represented by this heavy line, and a very well-developed island arc. In fact, it is so well developed, we refer to it as the microcontinent Avalonia. Clearly, it's going to have a massive impact on North America as it collides into it.
Back to the whiteboard. I want to focus on the upper part here of the sketch. This is the plate tectonic world before any of the collisions occurred. We've already talked about the Tectonic orogeny, represented by this island arc here and this volcano here with the subduction zone, and it collided in to North America. And it accreted on a terrain represented by blue here. It thickened the crust, as I've depicted here, and accreted on that terrain. Now we've learned that there's yet another subduction zone out here at the time with a larger landmass, volcanic landmass, and it had rivers and everything. I mean, it was a microcontinent. So it's going to be a much bigger collision when it comes. And that's depicted here. And this would represent the Akkadian orogeny that's going to occur because we have this microcontinent with some thickened crust, and it's a beefy guy. And it's going to collide too, and so it does. And I'll just draw that in right here. It puts on a big, nice terrain here. It accretes it on, and it thickens the crust and makes the mountains a little taller here, we'll say. Pretty significant, actually. That's when this accreted onto here. So now we're ready for the big collision of Africa with North America. This was to occur about 315 million years ago in the Pennsylvanian and is referred to as the Alleghanian orogeny. So this is just before it happened. Now, an important point is when the Akkadian orogeny occurred just earlier, okay, in geologic time just earlier, it forced the oceanic plate to break off and start subducting underneath Africa and creating volcanoes here. So we had magma rising up from the plate, right? Typical, and creating volcanoes along Africa, okay? And then it collided. And what a collision it was. With this continental crust coming in, it's a huge continent, it's more buoyant.
Continental crust has high percentages of silica and therefore is less dense and more buoyant.
It's going to make a massive impact and accrete a big terrain on, thicken the crust, make the mountains even taller. Try to do my artwork here. Himalayan style. That's what happens when you have continent-to-continent collisions. It makes gigantic mountains. And so they were much like the Himalayas. So as I put the final touches here on my sketch, we have Africa that has collided, accreted on the terrain. Of course, it's had a major impact on Africa. I'll put some mountains onto Africa here, much like the Appalachians. But of course, the Appalachians that we know are on North America, right here. And so we had that final scene, the great collision that created the magnificent Appalachian Mountains, much like the Himalayas. Just amazing to think about, isn't it? So here I have my Ron Blakey map, the maps I love so much to help us understand the world in the past. I have Pennsylvania outlined here to help us. These are the great Appalachian Mountains that had formed at the time, late Pennsylvanian age. And then the mountains over here were on the African continent. So the world at that time, just a magnificent chain of mountains. Just unbelievable, really.
This last collision also created a spectacular landscape seen here on the shaded relief map known as the Valley and Ridge Province. This geologic map shows the nature of this province even better, highlighting the wonderful patterns of folded rock formations. This cross-section shows the core of the Appalachian Mountains in this area, and then to the west, the Great Valley and Ridge Province, which is a fold and thrust belt.
The Valley and Ridge Province. You know, as a geologist and with my personal tastes, I see that province and those beautiful patterns, and I think about what is deep underground and what was once above ground that has since been eroded away, and it opens a whole world of fun for me. I want to help you see what I see. And to do that, let's start with a clay model. And here is that simple clay model that I want to show you. Just layers of clay that have been folded, several layers of clay, and an anticline here where the top bends over like this, and in the valley we call those synclines. So we have an anticline, syncline, anticline, nice and symmetrical, simple. The interesting thing is what we start to see as things erode and as erosion takes over when we have folds like this. Let me demonstrate. The second part of this story here with my model is I have taken these folds that we've seen here. I've put a sheet of paper through them like they've been cut. This would represent the land surface. And another thing I've done is I've tipped them a little so they're plunging under the ground. They're not horizontal to the ground, these folds. They're plunging underneath. This is very common. We call them plunging folds. Okay? And erosion is taking over and is going to cut down, down, down on a nice plane in this case, pretty much like a knife. And in general terms, that's exactly how it works. So let's do that. Erosion takes over and boom, the top part is gone. Now we're running around looking above. We're on here, walking around, driving our cars around. What patterns do we see on here? Let's take a look. That's what we see. So you're telling me that if I tip this back, where the surface of the land was, looking down, we're in an airplane here. Let me show you what we see. We see these beautiful fold patterns, don't we?
This geologic map in Pennsylvania shows some wonderful folding patterns.
Now, of course, we can have sharp folds that have different patterns, or folds that get bent, or they get cut by a fault and shifted around. We see all those things in the Valley and Ridge province. Really interesting and a lot of fun to think about. Now, another part of this is, well, okay, there are the patterns. We have the patterns. What about the valley and ridges? How does that happen? Let me show you. So the valleys and ridges, how do these ridges and valleys actually occur? Well, let's look at this cross-section of the world, should we? Of these folds. Cross-section meaning, let me sketch my famous tree here. Many of you will know about this. Put a tree here to make sure we're on the same page about what a cross-sectional view is. So here we have all this folded rock. Now, I've done a couple things here. I've put this black layer in with some hash marks in here, so it's pretty important in this story. And then these other layers. And of course, they go down deeper and deeper. Okay? Now, there are a couple key things I want to mention here before we get started with the power of erosion. And that is rocks that are resistant to erosion, like limestones and sandstones. I'll put a big thick layer of those in this black. It could be several of them. It doesn't have to be one, but dominated by, say, limestones or sandstones, resistant to erosion. The other units, the other layers that I've simply depicted underneath and above, we'll say that they're dominated by shales. Yes, you can have some thin sands in there or thin limestones, but they're dominated by shales and more easily eroded. So with that in mind, what happens as erosion takes over? So I have my eraser here. Let's start eroding. Let's see what happens. It's pretty straightforward. It's having a lot of fun early because all this stuff, all these layers stuff, they're easily eroded. It hasn't hit this hard layer. It's just having a ball. Erosion, primarily water, rivers, etc., ocean, beaches, and things, and or glaciers are very powerful at erosion. Wind, not so much. But here we go. We're coming along happy as we can be. The gods of erosion eroding along, just taking all this out. Now, it hits this sandstone and it goes, oh, I can't erode this fast. It slows down the erosion. But the erosion continues relatively rapidly down over here, right? And it just sitting here, it is trying to cut through this sandstone and or limestone layers, dominated layers. And it's having a difficult time. So it erodes down deeper here. But of course, eventually, these units get eroded too. So finally, let me start cutting into there. Okay? Let's do something like that. And it keeps eroding down in here. Keeps eroding. Keeps eroding. It's cutting through over here, erosion. But you see what's happening is we have a high area here because erosion can't occur as quickly relative to here. Okay? And I'll cut off just a little more. And it's cut way down on the flanks. And now let's put a new land surface and see what it's going to look like. this is the resistant cap, the ridges. Now, this is soft underneath, remember? So what happens? Well, it erodes a valley like that. It comes down and erodes a nice valley. And it could be more dramatic than this, of course. And over here, the erosion went to here, didn't it? Okay? So it strips back everything off this nice resistant formation here and pulls it down like that. Here, in this drawing that I have. And over here, this new surface, here's the cap, the big dramatic ridge that we get in the ridge and valley regions. And the erosion occurs, and it strips it back and comes along here like this. And pulls it back and makes a big low area. And over here, of course, it's going to erode a valley into here. And actually, I'm going to make this a little more dramatic. I want to just do that so we understand it just a little better. We're going to have that cap, and it's going to be a big old valley like that, okay, and a nice cap ridge. So, now here's the fun part. I've just removed that, and now you can visualize what it used to be like. And this is what I'd like you to do when you're out in that part of the world, when you're in the Appalachians, driving down a beautiful valley. If you notice rock formations tipping this way on one side of the valley, and this way on another side of the valley, in your own mind, you can go, I can visualize what that fold used to look like. It used to come right up over to the other side of the valley. And you can easily estimate how high it got up how high it once was. It's a fairly simple process. Now, of course, you can get into some nitty-gritty details and complications, but in general, it's pretty cool, isn't it? I mean, you can visualize that as you're driving around or hiking around. So in this valley, I've made this valley really wide. Well, if you're driving down this valley and you see rock layers dripping this way on one side and dipping down this way on the other side and big ridges, well, now you know, wow, this was a big valley at one time. And this ridge here used to go up over here and up over here. Or a big syncline, I should say, not a big valley. This was a big syncline at one time. So I hope that helps you visualize what the landscape used to be like and how it was created and how these ridges and valleys formed. To further embed this in your mind, I want to show you some beautiful ridges and valleys here in the desert of Wyoming, where it's very clearly exposed, and that'll help you as you're in the Appalachian region because they're so heavily covered by forests and beautiful grasses, okay? I'm walking along a ridge much like you'd see in the Ridge and Valley province. Let's pay attention to this ridge and see where it goes. Jumping to a nice elevation so we can see the big picture better, the arrow is pointing at the ridge where the Jeep is parked. Following this ridge, we see a beautiful fold pattern very similar to what we see in the Valley and Ridge province. Notice that there are many ridges and associated valleys. The ridge formation at one time went up and over like this and has subsequently been eroded away. Here the formation dives underground, forming a great syncline shown in blue, and then comes back up out of the ground to form another eroded anticline here in red. Using these principles, we now know that we have two anticlines and a syncline in view. And jumping to a geology map in Pennsylvania, I've labeled a series of anticlines and synclines. Now that we have a better perspective of these wonderful folding patterns that you see from above in map view, I want to come back to the clay model. So remember, we have, in this particular simple clay model, we have a simple anticline, syncline, anticline. And if you have erosion, if it's dipping into the ground, plunging into the ground, or like this down into the ground, so here's the surface of the ground, the map view's here. And what do we see? Really what we see in map view are kind of stretched out anticlines and synclines. So we have an anticline here, a syncline, and an anticline. It looks very similar to the front, only it's stretched, it's elongated. So if you look at Google Earth, or maybe you're in an airplane and you see these patterns from above, you know that's kind of what it looks like under the ground, just giant folds that aren't quite as stretched out like this. They're a little more compressed. Isn't that a neat trick? Back to a Ron Blakey map here to discuss a Foreland Basin, the Foreland Basin that developed during the uplift of the Appalachian Mountains. I have Pennsylvania outlined here. The border's somewhat suspect there on the east side. But at any rate, 450 million years ago, Ordovician period, the mountains had started to form or pretty well established. And see this little finger of deeper water right along here? That's what we refer to as a Foreland Basin. So here on my handy whiteboard with this sketch, I want to show you some of these principles of a Foreland Basin. This area here represents the Appalachian Mountains. Big, tall mountains. I show some thrust faulting in here where rock is thrust up and over each other, creating a big pile of rock. And then here I show the Foreland Basin. And what I've shown here is when it's at its maximum depth, so to speak, total, as far as total thickness of sediment within it. And that is 45,000 feet. Yeah, 45,000 feet. I still can't get over that. That is huge, huge thickness, isn't it? 8.5 miles. Okay, and then it tapers off here to the west. So how does this happen, this Foreland Basin? Actually, they're very common in mountain building, and it's very simple. When we add weight, we're stacking, we're thickening the crust, we're bringing rock and making it taller and taller into mountains. Well, it starts sinking into, it flexes the lithosphere, and so it sinks down. And think of it as a fairly rigid lithosphere, and when you're pushing it down, it's flexing this area down as well, which is right in front of the mountain, and that creates the Foreland Basin. But it does occur in phases or through time, and I want to show you that just for a second. I'm going to draw just a very simple Foreland Basin in early time. Nothing fancy. It's asymmetric, it's a little deeper here, and then it shallows out very gently. And that may represent kind of what this was early. And it had, it filled in with a little bit of sediment. Let me do that. So corresponding to this red here, it fills in something like this, okay? And we have water, of course, in this basin. The water depth may not have been all that great. It just depends. It varied, okay? So that's phase one. Well, you can imagine as you can continue to load that plate, the lithosphere, and continue to flex it down, this basin just grows. So in a second phase here that I'll show, I'll make the basin quite a bit bigger or deeper. Maybe bring it like that. Now we have these red sediments that in this early phase, so I'll put those in there. And now because it's flexing down, it bends that a little like that. So these represent those sediments. And the new layer of sediments could be covering a lot of time. The blue here, which is kind of like this, and so on through time. One interesting thing about this situation is geologists can look at the Foreland Basin and see the package of sediments, and they can date them and know the ages and the thicknesses and how the thicknesses vary and everything. And they can tell when the mountain took a big push up, because it flexes it more than before. And in this case, it was during the Akkadian orogeny when the biggest package that filled in, the basin dropped the most and filled in the biggest wedge. And they referred to this big thick wedge at that time in the Akkadian as the Catskill Delta. The uplift of the great Appalachian Mountains had far-reaching effects. And one of those is the generation of oil and gas and also the formation of coal. let me talk a minute just about coal. Uh, when the Foreland Basin is forming through time, as we've mentioned, with the mountains here, of course, the mountains are being eroded and shedding off material into the Foreland Basin, with deltas dominating on this side, and coastal plain environments where you have lots of swamps and creating great environments to create peat and then ultimately coal. Now, the importance, so that's one part of this, right? You have this space that's being filled in with these deltas, multiple ones, by the way, stacked through time as it fills in, one on top of the other, and filling on out to the west. Well, many, many layers of coal exist. Some of them are economic and some not, but let's talk about bituminous coal. So in order to create bituminous coal, you need to bury it about 10 to 15,000 feet because that's where the temperature gets high enough to form bituminous coal, which is around 185 degrees Fahrenheit or so and a bit hotter. Okay, so it forms, of course, at the surface at the time, or the peat does anyway, and as it starts subsiding in this Foreland Basin and more sediment gets on top, it gets deeper and deeper through time in this Foreland Basin as it develops, which means it's getting hotter. And finally, it gets to the level of forming bituminous coal. Now, anthracite is even more dramatic in that it has to get buried much deeper. Anthracite, for it to occur and form, has to be buried somewhere around 20 to 25,000 feet deep. So now you see you need a good Foreland Basin like this guy for that to happen, to reach the temperatures of 350 plus degrees Fahrenheit to form that anthracite. Now to the oil and natural gas. It has some similarities to coal in that you need burial depths for these hydrocarbons to form. So if we go into the case of oil, we need to understand where oil comes from. And it comes from the planktonic community in the ocean, meaning small animals, zooplankton, or plants, phytoplankton, that are microscopic for the most part, for the vast part of it. And they float around in the currents. The animals can swim a little, but not enough to go against current or anything. And as they die, they drift to the bottom of the ocean. And if you have a situation where the bottom waters are anoxic, meaning they lack oxygen, then those animals and plants can't rot away and they're preserved. And so you can have a mud layer or a shaly layer with, say, 5% organic material in there that's a great target or a great prospect for generating oil and natural gas. So as this organic-rich source rock is buried, kind of like the coal is, it's buried deeper and deeper, at around 8 to 15,000 feet, you're generating a lot of oil. And that's about 150 to 300 degrees Fahrenheit temperature is what you need. And for natural gas, you just keep it going down further and it cracks that oil that's there, plus, or converts that oil, is another way to think of it, plus it's generating from the source rock because it's so hot, because now you're buried at the 20 to 25,000 feet and your temperature is some 300 to 400 degrees Fahrenheit, where natural gas is being generated. So isn't that fascinating? We need this Foreland Basin to help us not only have an environment that's good for life, for the trees and planktonic community and all this going on, we also need it to help us bury it to the proper depths so that we can have hydrocarbons in our lives and energy in our lives. The last far-reaching effect of the Appalachian Mountains that I want to talk about has to do with erosion and deposition, and this is so important. To do this, let's walk through some time maps from Ron and Blakey, my favorite maps. The world in the Ordovician 450 million years ago. We see the early Appalachians have occurred, the Tectonic orogeny, and notice the shallow seas all through the United States and up north into Canada. Just amazing to think about, entirely covered with water. This occurred after the melting of the great glaciers of Snowball Earth, and the waters came up from the melting of those glaciers, and the land surface had been weathered down and eroded down, and the water covered everything, essentially. The second map I want to show you is in the late Pennsylvanian. And now we have the full glory of the Appalachian Mountains here, prior to Africa pulling away, rifting away. And notice we're starting to fill in the seaways. And the Appalachian Mountains played a big role in this, to start filling in to the west. And my last time slice that I want to look at is in the Triassic 245 million years ago. And this is just as Africa was starting to pull away, just the initial stages. Full, big, giant mountains of the Appalachians. But notice what's happened. We have continually filled in more and more sediment, filling in the continent, creating a firm footing for us to, well, build our homes on. This is really important to our future, isn't it? And to where we are today. So the Appalachians dominated this process. You know, was a really interesting study down in Arizona where they were looking at tiny, tiny zircon crystals, which are very durable and can handle the erosive forces of rivers, that were carried clear down into Arizona. And they can look at the chemical signatures in there, and they determined that indeed they did come from the Appalachians. Wow, that's just really neat, isn't it? I hope you've enjoyed learning about the geology of the great Appalachian Mountains. Thank you for watching this video.